Any questions or comments before we get started for today? A group of mathematicians and a group of engineers are traveling by train one day to go to a conference. Each of the engineers buys their own ticket, but only one of the mathematicians buys the ticket. Of course, the engineers are ridiculing mathematicians, saying they're going to get into a lot of trouble, when suddenly one of the mathematicians yells, "Hey, the conductor's coming!" All the mathematicians quickly disappear into a single restroom. The conductor checks the ticket of each engineer, knocks at the restroom door, and says, "Ticket, please." So the mathematicians slide their one ticket under the door. Conductor checks it, leaves. A few minutes later, when the coast is clear, mathematicians come out of the restroom, and the engineers are very impressed. When the conference ends, the engineers decide that they are just as smart as the mathematicians. So the engineers buy just one ticket as well. This time the mathematicians get on board with no ticket at all. Engineers are starting to question the mathematicians when suddenly one of the mathematicians yells, "Hey, the conductor's coming!" This time all the engineers quickly pile into one restroom. A few seconds later, one of the mathematicians knocks on the restroom door and says, "Ticket, please."
Oh my god. Wow.
Alrighty, and with that, it is quiz time. So as per usual, go ahead and put everything away. Have fun. Go ahead, take a few seconds to finish up your thoughts. And pass your quizzes in, please. Quizzes in, please. Alrighty. So, plan for today. Let's say we want to know what square root of 4.2 is. In other words, what real number, what positive number, if I square it, will give me 4.2? James, you know what that is offhand? I don't either. It's not a nice number. We'll put that. In fact, it's irrational. It can't be written as a nice fraction. So, and if I were to ask you to find square root of 4.2, what would you probably do? Ooh, okay. How would you approximate it?
Well, I know that square root of 4 plus 2.
Mm-hmm.
So, and 4 plus 2 is 4, so 4 then is 5.
Okay.
Round down, I guess. That would be exact.
So you think it would probably be something a little bit over 2? Sounds reasonable. Square root of 4 is 2. 4.2 is pretty close to 4, a little bit bigger. So we would expect square root of 4.2 to be a little bit bigger maybe than square root of 4, which is 2. Sounds reasonable. Let's say we were engineers and we were building a bridge. And not the sort of silly engineers like all in all my jokes of the day, but actually serious ones who want to do a good job of it. Very good. If I were to come to you as an engineer and you were to say, I need to know what the square root of 4.2 is so I know how long to make this bridge pylon so that it'll structurally stay supported. If I came to you and asked that, and you said, oh, square root of 4.2, it's probably a little bit bigger than 2, would you be happy with that answer?
No,
Why not?
because it's not accurate enough.
It's not accurate enough. I mean, it's certainly true. I think what Anna said, square root of 4.2 is a little bit bigger than 2. But it's not very accurate. So how can we get more accurate? Right? Plug it into a calculator. Brilliant. We're going to plug square root of 4.2 into a calculator where the calculator will say that the square root of 4.2 is approximately 2.0494 ... And I don't know, Reagan, if I were to tell you it's 2.0494 ... would that satisfy you?
Yeah, that'd be better.
It would certainly be better. Is it close enough? I don't know. It depends on some engineering that I, as a non-engineering person, do not really know. But it would certainly be a lot closer than being able to say it's a little bit bigger than 2. So here's a question. How does the calculator know that? Does the calculator have that number memorized? Gabe, what do you think? You don't know? Well, square root of 4.2 is not a nice number. In fact, if you were to write it as a decimal, it would be a decimal that keeps going on forever, never repeating itself. It's not a very nice decimal. But the question is, how do we know? How does the calculator know enough to just give you the first 10 digits? Because calculator is not, because your calculator, I don't know, if you have the newest TI-80 whatever contraption, it's a pretty powerful piece of technology. It does not know the square root of every single number in spite of that. So what we're going to be talking about today is kind of a method that uses some of the tools from calculus that we've been building up so far to be able to come up with a pretty good approximation. And Reagan, I'll let you be the judge at the end of the process whether the approximation we found is pretty good or not. And so the idea in this standard is going to be, how can we use the idea of derivatives in the tangent line to a function to help us approximate a number like square root of 4.2. So with that, let's jump into standard 14. 1, 2, 3, 4, 5, 6. 3, 4. So here's what we're going to do. Let's look at a, actually I'm going to make this bigger. I want to make this big because we're going to be looking at this graph quite a bit. Let's take a look at the graph of y equals square root of x, which is going to look something like this. This is our function. And it's going to keep going, but slower and slower as time goes on. And what we want to do is, if we want to look at, let's say, the point x equals 4.2, which is about right there, I want to know what is the y coordinate of that point. Problem is, square root of 4.2, as we've said, not a very nice number. So what we're going to have to do is, our first step is going to be, let's find a value of x that's close to 4.2. That's a lot easier to plug into the square root function. So in other words, I want to start by finding a value of x near 4.2 that's nice. Something that we can plug in, something that we can take the square root of without too much fuss, muss, or cocoa nuts. Anybody have an idea for a value of x close to 4.2 that's relatively easy to take the square root of? Katie?
4.
4? And I think you suggested this earlier, compare square root of 4.2 to square root of 4. Yeah, square root of 4 is something we know how to find. It's a point that is pretty close to 4.2. Note that this graph is not drawn to scale, or otherwise it would be very hard to make anything out on it. And we know that square root of 4 is going to be 2. Square root of 4, 2. Pretty straightforward, easy to calculate. A lot easier than square root of 4.2 for sure. So the idea that we're going to be looking at, I want to find a tangent line to this function at x equals 4. Because I think we have, or we can find enough information to find a formula for the tangent line And our idea is if this is f of x equals square root of x, and this is going to be L of x, which is going to be the tangent line to f of x at x equals 4, I think what we can do is square root of 4.2, or f of 4.2. Let's say, for the sake of argument, we haven't plugged that into a calculator yet. We don't know what square root of 4.2 should be equal to. But what we can do instead is, if you notice, the tangent line in f of x, the tangent line at x equals, taken at x equals 4, if we were to plug 4.2 into this tangent line, I think we can actually do that a lot easier, because plugging 4.2 into a linear function is not nearly as bad as trying to plug it into a square root function. So our idea is going to be to use L of 4.2 to approximate f of 4.2. And in order to do that, what we're going to need to do is we're going to need to find a formula for the tangent line to our function f of x, taken at the point x equals 4. We'll talk about why at x equals 4 and why not at x equals 4.2 in a minute. All right, I'm going to find a formula for a line. Time for some high school mathematics. What information do we need to find a formula for a line? Morgan?
Slope and y-intercept.
Slope and y-intercept. So y equals mx plus b, in other words. If we know what the slope of our line is, we know what the y-intercept is, the point over here, or the y-coordinate of the point where x equals 0, we should be able to then find a formula for the line from that. Groovy. Let's work with that. How do we find the slope of this line? This line is given by the tangent line to our function, taken at x equals 4. Let's see. How do we find the slope of that? Pardon?
Take the derivative of the square root of x and plug 4.
Holy smokes, you want to take f prime of 4? Yeah, because by definition, if you remember all the way back to standard 4, when we first started talking about what does the derivative tell us about a function, we said that the derivative to a function gives us the slope of the tangent line to that function geometrically. So then, in other words, by definition, the slope of our tangent line is going to be m equals f prime of 4. Because if we know what the slope is to our tangent line at x equals 4, well, we can use that in Morgan's formula for slope-intercept form to tell us what we plug in for m in finding a formula for our tangent line. So let's do that. So our f of x is going to be square root of x, or x to the 1/2 power, if you prefer. What's going to be f prime of x if f of x is square root of x? This is one we've seen a bunch of times now. Charlie?
1/2 x to the negative 1/2, or 1/2 square root of x.
Yeah, it's going to be 1/2 x to the negative 1/2, which is the same as saying 1/2 square root of x. Which means that if we want to solve for our m here, we would get m is equal to f prime of 4, which is 1 over 2 square root of 4, which is 1 over 2 times 2, which is going to be 1/4. So in other words, we know exactly what the slope of this line is. It's going to be equal to the derivative of our function f evaluated at x equals 4, which is going to be equal to 1/4, or 1 over 4. Any questions or comments thus far? I've got a question. What's the y-intercept? In other words, if we were to plug in x equals 0 into this line, what would be the y-coordinate of that point? James?
We can find it by plugging in L of 4
Okay.
into the y equals 1/4 x plus b.
Okay.
So
I have a slight issue with that. So if we're plugging in 4 into our L of x formula, so 1/4, right now we know that our tangent line is formula 1/4 x plus b. You want to plug in 4 into that? Problem is, I don't know if we could evaluate that without knowing what b is. Is that a Norm?
So we don't know what B is, but we know that it's all linked to, right? So we're plugging the coordinate 11.2.
Ah, so in other words, you're saying that we know that 4, 2 is a point on this line? Because, well, it has to pass through the same point at x equals 4, it passes through f of 4. So we could plug in 4, set that equal to 2, and solve for b. Man, this has gone a different direction than what I had intended. Do I want to do that? Do I want to do that, Nora? Okay, well, I want to do that carefully. Okay, so if we do that, we would get 1 plus b is equal to 2. Oh, hey, b is equal to 1. There's a way, though, that we could have done this, that we didn't need to find b at all. Let's say we didn't know what b was. I'm going to cross all of this out. Nora and James, the approach that you all suggested does in fact work, and is going to give us the same formula for a line that using the other approach that we're going to have. Truth be told, there's a little bit easier way to do that. Does anybody remember another way to find a formula for a line other than using slope-intercept form? Nora made an interesting point earlier, that we know that 4 comma f of 4, which is equal to 4 comma 2, because f of 4 is square root of 4 is 2, is a point on our tangent line L of x. And that L of x has a slope of 1/4. Jonah?
did point slope form?
Yeah. A way to do this that's maybe a little easier, rather than having to go through the process of solving for our y-intercept, is we could use, we have a point on our line, 4 comma 2. We have the slope of our line, which is 1/4. Well, if we have a point, and we have the slope, we could just use the point-slope formula for a line. By any chance, Jonah, do you remember what that formula is?
I know what it looked like. I have an image of it, but I can't
the signs, I'm not sure where they go.
Ah, Jonah has a picture in his head. So, here's a little bit of a quick review. A line passing through a point, let's say x naught comma y naught, with a slope of m, is going to have a point slope formula y minus y naught is equal to m times x minus x naught. So let's see what happens if we use that formula here. So what we know about our tangent line is that we have a point on our tangent line of 4 comma f of 4, which is 4 comma 2. We know that we have a slope of n equals, well, I just erased it, but it's n equals 1/4, which we got from just taking f prime of 4. So if we treat 4 comma 2 as our x naught comma y naught here in this case, what I think we can do is we can take our x naught comma y naught of 4 comma 2 and our slope of 1/4 and plug that into our point slope formula for a line. And that way we don't actually have to go about solving for our y-intercept. We just plug in this information that we know into this formula that we are given. And if we do that, what we're going to be left with is going to be y minus our y naught value is 2 is equal to our slope 1/4 times x minus our x naught value, which is 4. Which is the same as saying y is equal to 2 plus 1/4 times x minus 4, which is the same as 2 plus 1/4 x minus 1, which is the same as y equals 1/4 x plus 1. Using the point slope formula for the line. Y minus y naught equals m times x minus x naught. We know what the m is. That's the slope of our tangent line. It's just f prime of 4. We know what an x naught comma y naught, a point on our line, is because the tangent line and the function have to meet up at this point. So we just get square root of 4, or 2. And so if we know a point on our line and we know the slope, we can use that to find the point slope formula of our line. And then if you want, because I know so many of you all in the audience are twitching to say, Dr. Gersel, I like slope intercept form. We can simplify it down to slope intercept form if it makes you feel better about yourself. Any questions or comments about what we've just done so far? So, Dr. Gersel, where are you going with all this? I thought we were trying to find square root of 4.2. Well, if you remember, we had this idea earlier on, which is to say, use the tangent line, use L of 4.2 to approximate F of 4.2. Because if you notice, at this point here, 4.2, the tangent line, L of x, and F of x, our original function, are pretty close to each other. In fact, they're a lot closer to each other than what this graph is, how I drew this graph, because I needed to kind of exaggerate distances in this graph in order to make it so that you and all of you, especially those of you sitting towards the back of the room, can actually see the difference. But if we want to use L of x, L of 4.2, to approximate f of 4.2. Dr. Gerstle, what does that even mean? Well, I'll tell you. It means I need a smaller piece of chalk so I don't start making big squeaky noises. It also means that if we wanted to try and evaluate square root of 4.2, well, that is equal to f of 4.2. And according to the work that we just did, f of 4.2 should be pretty close to L of 4.2. Okay, Dr. Gerstle, what is L of 4.2? Did I draw two lines here? It's hard to see. Well, if we look back up here at the board, when we found our formula for our tangent line, we got y equals 1/4 x plus 1. Turns out, that's the tangent line that we were looking for. And so if we want to find what is L of 4.2, we could just take 4.2 and plug it into our tangent line and get 1/4 times 4.2 plus 1. And I don't know about you all, but taking square root of 4.2 is scary. Taking 4.2, dividing by 4, adding 1, that sounds a lot less scary to me. Right? Because, let's see, that's half of 2.1, which is 1.05. And there's our approximation, 2.05. So what did we just do? We said square root of 4.2 is hard to find. Let's pick a nice point close to 4.2, like 4, for instance. I think is what Katie and Anna had picked out as sort of a point that's close to x equals 4.2. That's a lot nicer to take the square root of than 4. And what we did was we found the tangent line to our function at x equals 4. And then we said that, well, at x equals 4.2, the tangent line and the original function should be pretty close to each other. There's a very small gap between them. And so finding L of 4.2 should be a lot easier than finding f of 4.2. So we can approximate this value by using this value instead. All right, Reagan, come back to you for a minute. You are the engineer in charge of this project. You've asked me what square root of 4.2 is. And let's say you're testing me, so you already know that it's about 2.0494 ... Let's say I told you, I did some approximation method and found that the square root of 4.2 should be about 2.05. Did you say that's a pretty good approximation?
Yeah.
You think so? It's about 0.0006 ish off from the actual value. Is that close enough for building a bridge?
Probably not. Maybe.
Possibly.
I mean, depends.
Depends on how exact you need.
Yeah.
And if you take your appropriate engineering courses, you'll get a sense of how good an approximation is that. Here's how a calculator essentially works. If you want to know how does a calculator give you a number for square root of 4.2, what it does is it does a bunch of calculations behind the scenes, sort of like this, to say, square root of 4.2 I can approximate as being about this value. I'm going to give you this value, and not the actual square root of 4.2, because the actual square root of 4.2 goes on forever. Calculators aren't good at going on forever. It's going to approximate it for you and say this number is close enough. Calculator does not have square root of 4.2 memorized. Instead, what it does is it does some trickery like this behind the scenes to give you a number for square root of 4.2. But Dr. Gerstle, my calculator gave me 2.0494681327 ... This only gave me 2.05. Why is the calculator so much better than yours? Well, first of all, get off your high horse. Second of all, a modern calculator has methods for doing this that are give much better, closer approximations than what the tangent line does. For instance, what a calculator might do is instead of finding a tangent line approximation, it might use a tangent parabola, or a tangent cubic approximation, or a tangent quartic, or a tangent quintic, 3, 4, 5 polynomial. And calculators have ways of making this a lot more precise, and so do we if you go on to take Calculus 2 and look at Taylor series. But the idea is calculators don't actually know how to find this number exactly. Instead, it approximates it using a bunch of behind-the-scenes calculations that it doesn't show to you. And modern calculators are pretty good at doing it quickly. So when you type in square root of 4.2, click enter, beep. First of all, turn the volume down on your calculator. I don't know why it's beeping at you. Second of all, it'll just take a split second to come up with a number like 2.05. Except your calculator will do a much better job of it than what we did. Questions, comments, concerns? I've got a question. Let's say we wanted to use this tangent line to approximate square root of 17. Spoiler alert, square root of 17 is not a very nice number. I'm on the second page in the packet now. I want to follow along there towards the bottom. I'll come back up towards the top here in a second. Let's say we wanted to try and approximate square root of 17 by saying, square root of 17 is equal to f of 17, which should be approximately equal to L of 17, which when I plug in 17 into our function, we get 1/4 times 17 plus 1, which is 17/4, that's 4 1/4, so that's 4.25 plus 1. And that would give me an approximate value for square root of 17 of 5.25 if I were to plug 17 in for x into this function. Before class, I tried plugging in square root of 17 into my calculator. And what I got when I plugged it into my calculator was f of square root of 17 is approximately 4.123 ... Hey, Reagan. Do you think that this is a pretty good approximation for that?
No.
No? Why not?
There's way too much of a difference.
Yeah. Whereas this number was only about 0.0006-ish off from this number. So our tangent line approximation for square root of 4.2 was pretty good. Our tangent line approximation for square root of 17, well, that's a full unit plus off. What's up with that? Why was our 4.2 approximation so good, but our 17 approximation was pretty awful? I want you all to do is take a minute or so, talk to your neighbors, and see if you can answer the question of why was our square root of 4.2 approximation much, much more accurate than our square root of 17 approximation? So go ahead and talk to your neighbors and see if you can find an explanation for what's going on here.
Yeah, radical. Wow, there gets away. Or was it 4.2 because they're right next to yeah, so you knew. Yeah, that'd be a lot.
New L. Is that like
Give me the look of, please don't look at me. No, that's okay. I like it when students have that look nice. It makes it easier to find someone to hone into. Why? So let's come back together. Why is the square root of 17 approximation so much worse than our square root of 4.2 approximation was, do you think? Our square root of 4.2 approximation was off by about 0.0006, whereas our square root of 17 approximation was off by, I don't know, 1.13-ish. What's up with that? Eden?
Because your original function is curved, you have to draw a new tangent line for a new point.
A new tangent line for a new point, because our original function was pretty curvy. Yeah, so let's look at 17. Again, this graph is very much not drawn to scale. Here's where f of 17 is, which is where our square root of 17 would be. Whereas if we wanted to find what is L of 17, that's going to be the y-coordinate of this point about right here. Morgan, what do you notice about how far apart f of 4.2 and L of 4.2 are versus f of 17 and L of 17?
17 is much farther away from F of 17.
Then L of 4.2 is from f of 4.2?
Yes.
Yeah, these 2 points have a pretty small distance from each other. In fact, much smaller than what my not-to-scale graph would suggest. Whereas these 2 points, there's a pretty big distance here of about 1.13-ish. Whereas this distance is about 0.0006-ish. In other words, just looking at our graph, our tangent line, taken at x equals 4, is going to do a much better job of approximating f of 4.2 than it is to approximate f of 17. And the reason why is because we took our tangent line at x equals 4, which is much closer, I would say, to 4.2 than it is to 17. Because we may have taken our tangent line at x equals 4, but the further away you get from x equals 4, the further and further the tangent line, L of x, is going to get from our original function, f of x. So that if you look at points that are close to 4, like 4.2, the tangent line hasn't had very much time to get far away from the graph of our function. Whereas if we go all the way out here to x equals 17, which should really be like out here somewhere, the tangent line has had a lot of time to get farther and farther away from our actual curve. So we can say at 17, the tangent line has had a lot further time, has had a lot more time to get far away from f of x when we get out to 17. Whereas at x equals 4.2, the tangent line and f of x haven't had much time to get diverge from each other, to get far apart from each other. So naturally, our approximation at a point much closer to x equals 4, we would expect to be a much better approximation than if we were to try and use this tangent line at x equals 4 to approximate f of a point that's really far away from 4. Any questions or comments about that? I've got a question. What could we do if we wanted to find a better approximation to square root of 17? Using our tangent line at x equals 4 gave us a pretty poor approximation, according to Reagan, for what square root of 17 should be equal to. How can we find a better approximation? James?
Do it at x equals 16.
Do what at x equals 16?
Take the square root of it and use the linearization method.
Oh, so in other words, take a tangent line at say 16 instead?
Yeah.
Yeah, so if we wanted a better approximation, what we could do is to take a different tangent line to our function at a nice point that's a lot closer to 17, say at 16. 16's fairly close to 17, a lot closer than 4 is. And 16 is also a nice point that we could find the tangent line, and I think that would give us a pretty good approximation as well. So, how do we find a general formula for what our tangent line is going to be? Because this is what standard 14 is all about, is using tangent lines to approximate values of functions that are hard to plug in directly. 4.2, hard to plug into the square root function, a lot easier to plug into our L of x function, because L of x is linear. Plugging numbers into a linear function is something that computers can do extremely easily. Something that humans probably do a lot more easily than plugging it into the square root, at the very least. So, in general, we're going to call this approximation the linearization method for approximating values of a function. And we're going to say, let's write it over here so Lauren has some hope of seeing it. Sorry, song lyrics. we're going to say that the linearization of a function f of x at the point x equals a is just going to be the tangent line taken to f of x at the point x equals a. So linearization is a fancy word that just means tangent line. But if you go on in math, you'll hear, oh, linearization. The idea behind tangent line is when you take a tangent line to a function, you're coming up with a line that sort of approximates how is your function behaving near the point at which you're taking the tangent line at x equals a, in this case at x equals 4. And so linearization just basically means if our function were to behave like a line, what would be that line at this point? And the formula that we can use to find a tangent line approximation at a point A is going to be L of x is equal to f of a plus f prime of a times x minus a. That's going to be the formula that we're going to be able to use to help us make find a formula for our tangent line. And so then the idea is, if we want to approximate something like square root of 4.2, we find a nice value of a near 4.2. We find a tangent line approximation to f of x, or a linearization of f of x at that nice point. And then we plug in 4.2 in for x in order to get our approximate value. Well, Dr. Gerstow, where does f of a plus f prime of a times x minus a come from? Turns out that formula just comes from the point slope formula. Y minus y naught is equal to m times x minus x naught. Because the tangent line to f of x at x equals a is going to have a slope of m equal to f prime of a. That's just by definition. F prime of a is the slope of the tangent line to f of x at x equals a, literally by how we defined derivative back in standard 4. And our tangent line to f of x at a is going to pass through the point x naught comma y naught is a comma f of a. Why? Because our tangent line, if we're taking a tangent line at say a equals 4, our tangent line and the actual function f of x should meet up at 4, at the point A at which you're taking your tangent line. So we know what the slope of our tangent line is, it's f prime of a. We know that a point on our tangent line, x naught y naught, is going to be of the form a comma f of a. I claim we can use that then to find what's our tangent line formula going to be, using point slope formula. So using point slope formula, turns out that we're going to get that y minus y naught is equal to m times x minus x naught, as before. If we plug in our x naught, our y naught, and our n values though, we know y naught is equal to f of a, our m is equal to f prime of a, our x naught is equal to a, and that's just coming from the fact that a comma f of a is a point on our tangent line, and f prime of a is the slope of our tangent line. And then if we add f of a to both sides, we get y equals f of a plus f prime of a times x minus a. And that is what we're going to call our L of x formula for our linearization. And that is the straightforward-ish way to find a tangent line to a function at a point. Ugh, that's an awkward amount of time left. I wanted to do one more thing. Any questions or comments? Everybody's putting their stuff away as if I would let it go for 3 minutes early. Yeah, bro.
So would this quiz be after the exam on Friday?
Correct. Yeah. So on Wednesday's class, we're going to look at a bunch more examples of putting this into practice, finding tangent line approximations or linearization approximations to functions. First time you'll be tested on this will be on Friday's exam, and then I'll probably give you all a quiz next Monday or something on Standard 14. That's correct. That's close enough. Have a good day, everybody.